Hi there! In this video, we will be covering Chapter 1, which is on logic and proofs. Specifically, we will be covering Section 1.7, which is an introduction to proofs, and a little bit of Section 1.8, which is on proof methods and strategy.
A proof is defined as a valid argument that establishes the truth of a statement. The statement that we are proving or disproving is usually called a theorem. Let's learn 3 methods to prove a theorem. The first method is called a direct proof. A direct proof is pretty straightforward. You're not making any new assumptions. Here's how it's done. Start with a P that you assume is true. Using established facts called axioms, logical equivalencies, and rules of inferences, prove that Q is true. Let's try an example. We start with a theorem. If n is an odd number, n squared is an odd number. To prove this, we start with the assumption that n is an odd number. This is our P. Our Q would be what we are proving, which is n squared is an odd number. To start proving this, recall that n equals 2k plus 1 for an odd number. We can plug this into the formula n equals n squared. Solving this out, we can replace 2k squared plus 2k with the letter r. This will equal some integer. Knowing that r will equal some integer, we are left with the equation n squared equals 2r plus 1. Remembering that an odd number is equal to 2k plus 1, we can see that n squared would equal an odd number. This proves that if n is odd, then n squared will also be odd.
The second method we will be learning is proof by contrapositive. Another name for proof by contrapositive is indirect proof. Based on logical equivalence, if not Q, then not P is a true statement, then if P, then Q must also be a true statement. First, one must assume that not Q is true, and use logic to show that not P is also true. Then, using the definition of contrapositive that was learned earlier in Chapter 1, it can be concluded that if P, then Q is also true, thus proving the theorem. The contrapositive method works because a statement cannot be both P and not P at the same time. Now let's try an example of the contrapositive method. The question is, we need to prove that if n is an integer and 3n plus 2 is odd, then n is also odd. First, we must assume that n is even, or not Q, making n equals 2k for some k by the definition of an even number. Then we use that n, substituting it into 3n plus 2, or P, and then we use algebra to get to our final statement that 2 times 3k plus 1 equals 2j, for j equals 3k plus 1. Therefore, the statement 3n plus 2 is even. We have shown that if not Q, then not P. Then, by the definition of the contrapositive, we can conclude that if P, then Q, or the statement if 3n plus 2 is odd, or not even, then n is odd, or not even, thus proving. Let's try one more example of the contrapositive method. This question states, prove that if n is an integer, if n squared is odd, then n is odd. We can prove this. To solve this, much like the last problem, we assume not Q, or n is even. By the definition of an even number, we can state n equals 2k for some integer k. Then we sub this into n squared. Then, using algebra, we get to the statement 4 times 2k squared. This also is even, making the statement n squared even. Therefore, we have proven that not q, then not p is true, and by the definition of the contrapositive, if n2 is odd, n must also be odd.
Contradictions are the third type of proof that we will look at. Proof by contradictions are considered indirect proofs because they do not prove results directly. Our first step in these types of proofs is to assume not P to be false. We must then derive a contradiction. Because the statement R and not R is a contradiction, we can prove that P is true if we show that not P implies R and not R as true for some proposition R. Let's look at an example. Prove that if you pick 22 days from the calendar, at least 4 of these days will fall on the same day of the week. As with all contradiction proofs, we will assume not P. That is that no more than 3 of the 22 days fall on the same day of the week. Because there are 7 days in a week, this implies that at most 21 days could have been chosen. This contradicts the assumption that we picked 22 days. We now know that P is true, and at least 4 of the 22 chosen days fall on the same day of the week.
Proof by cases is a method to prove statements where all cases need to be proven true for Q. So P1 or P2 and all the way to Pn would need to be proven so that Pn then Q. Prove that if n is an integer, then n squared is greater than or equal to n. Case 1 is n is equal to 0. Case 2 is n is greater than or equal to 1. And case 3 is n is less than or equal to 1. In case 1, n is equal to 0, and 0 is equal to 0. In case 2, n is greater than or equal to 1. And when we multiply both sides of n is greater than or equal to 1 by n, we get n times n is greater than or equal to n times 1. So n squared is greater than or equal to n, so that's true. In case 3, n is less than or equal to negative 1. So any number squared is going to be positive, so that is greater than or equal to 0, so that's true.
Additional proof methods that will be learned later on include mathematical induction and combinatorial proofs. From this video, we hope that you now know proofs. Thank you, and thanks for watching.